Okay. So I covered using modules, and then containers are important, and the accounting models too. But I guess that will be some kind of self training for you guys. But anyway, we will be around for questions later. It's not the only chance to learn things. By the way, tomorrow I will continue, I guess, with some part of this early in the morning from 9 to 11, and then at 11, Pascal should be joining, basically to have a conversation with you guys about the many questions that you may have. So just have an open mind and review what kind of questions have appeared or do you have for your projects into going into the future. But also Pascal want to discuss some of the things that we don't want you to do. So do's and don'ts, because yeah, basically the supercomputer is a shared resource, and one of the typical issues we have are users overloading the loading nodes, as I said, but also consuming resources that they should not be consuming, etc. So basically, this kind of conversation is coming tomorrow at 11, around 11. But as I said, also, I guess conversation means also questions from you. So yeah, just get ready for that. So I will jump to module 8, which is the schedule of jobs. 8 and 9 are the things that we are going to cover today. And then tomorrow we're going to cover 11 and a module that is not here, but it's in our documentation, which is the use running jobs on the GPU partition. Okay, so scheduling jobs. So basically, you will learn here what is a job scheduler and why we need a job scheduler. Then check this important grouping of the nodes that we call partitions. And another very important feature of the scheduler are the queues. Well, the job queues. So let's go for it. So basically, so the first job is the computational work that needs to be executed in the supercomputer. The job scheduler is the software entity, if I can say, a program that manages those jobs. So it put them in a queue, it gives some priority to the job and decide what goes first and where to run it. There are many different schedulers. The one that they use in NCI for GADI is PBS. Here we use Slurm. Those are the two most used schedulers around supercomputing centers around the world. But some new schedulers are coming. So yeah, I know that for El Capitan supercomputer that is coming next year, and it's going to be #1 in the list when it is launched. It's not going to use any of those. It's going to use their own scheduler because all of them have some pros and cons, and they rather develop their own scheduler. But the idea is basically it's the manager of the supercomputer in terms of execution of jobs. Yeah, the warning again to don't do computation in the logging nodes. So how is a job scheduler useful? So imagine just you're planning your available time and days. In this case, a typical manager. So this is graphics showing jobs in different colors. So what we have in the x-axis are the different cores, and we have in the y-axis, and in the x-axis is time. So what you can see is, for example, these sort of fat jobs are using cores from around the, let's say, the 6,000 to, let's say, this, yeah, 6,000 to the 7,000. I don't know. So it's a fat job. It uses many cores, and it uses them for around 8 hours. So this is a large job in terms of number of cores using and in time. And after that one, another one of the same size of cores started again. Probably the same job, restarting after it finishes, restart again. This is very common. So jobs in Setonix have a maximum time limit of 24 hours. So probably this job started 24 hours earlier, and when it reached the wall time limit, it finished. But somehow the user that scheduled this job also said that once it's finished, there is another job that if the scheduler wants to and has resources available, can restart immediately from the point this one finished. So what jobs need to have are what we call a checkpoint to basically save the results in a way that the job can restart from those results. Those results are saved in Scratch in the file system. So the job can restart. So it reads whatever status the code, the simulation had, and restart again. There are some other wider jobs and some other more thinner, which use less resources in terms of number of cores, and probably some other that runs for just a couple of hours or for even less, for minutes, etc. So all this Tetris kind of idea, the scheduler needs to be aware of. So basically, for example, to run this even wider job, it needs to find space. Sometimes the scheduler decides to not run anything and just wait for some other jobs to finish for starting a job that needs more cores. So it plans in advance. So all these jobs were previously submitted to the scheduler, and the scheduler does not have them running, just have them in the queues. And the scheduler knows, okay, I have this in the queue. This job will need this amount of resources, so I will try to make space. I can run these little other ones before it to make some space, etc. So basically, this all complex idea to have the supercomputer busy and fully busy all the time. So that's the plan. So the plan of the scheduler is basically use the resources, the hardware resources that are very expensive, use it the most, the more you can. Any kind of resource that is idle and not idle at any point is just bad use of resources. Yeah, so when you submit a job request, not immediately, the scheduler needs to think a little bit, but in a couple of minutes or so, it gives you back an idea of when your job can start. And when you submit a job, you tell the user is the one that needs to know how long it's going to take. So that is based on your own experience, on how how big is your problem, your own code, etc., and you know how much time you will need. So you ask for that time. If you know that you're not going to need the 24 hours, you say, okay, my job is going to run and only use 2 hours. And that is very useful for you and for the scheduler, because the scheduler knows that even if it's a wide job, it's going to take a short time already specified by the user, and it finds places where to put it. If you don't use the whole time, then it will think that the job is going to be long, 24 hours, and that creates problems. So it's always very important for the users to tell the approximate time, close, very, very close to how much time it will take. So yeah, to maximize efficiency, yeah, I guess that's the idea of the scheduler. I don't know if you have any questions here. And when it finishes, it also tells you somehow. You can ask to send you an email, but usually users are checking all the time their jobs, if they are running or if they have finished by themselves. Log into the login nodes and query the scheduler, where is my job? How is it going with my job? And it will give you the information back. I think that's what we are going to learn in this module. So yeah, the idea is to plan yourself, and also is to not just wait for jobs to start. So you can plan, you can send many jobs at the same time, or jobs chained, as I was sort of thinking about this purple and green. So you can submit these two jobs in a chain. So this job will wait in the queue until this one is finished, and the scheduler may know that there is space and they will put them together. If not, that one will run, the green one may run later somewhere else. Like for example, this yellow one. Probably this was the first one. This has nothing to do with the purple. It is the yellow one that is restarting after this one finished, but couldn't restart immediately, needed to wait for some time to restart again. Okay, so the scheduler has assigns different priorities to the jobs. So it is relative to allocation. So that means allocation is the amount of resources that were granted to the project. So as the project consumes their allocation, the scheduler gives to them less priority. So let's say that a project has already consumed 80% of their allocation, and then there is a project that has not consumed anything and submits a job, both submit a job at the same time, then the one that has already consumed 80% of their allocation has a lower priority than the one that hasn't. Also, once jobs were submitted, received by the scheduler, and putting them in the queue or the waiting queue, is if the job was submitted a day ago, that one has a higher priority than any job that can be submitted now. So those one were already waiting longer in the queue, those have a higher priority. Also, the scheduler prioritizes jobs that use a lot of resources. So we sort of not like jobs that will only use a couple of cores. We like jobs that want to use thousands of cores at the same time. So at the end, that's the idea of the supercomputer. We have a large number of nodes with a large number of cores, with a very efficient interconnect with them, among them. Basically, all that infrastructure is prepared to run big jobs. So if you want to run jobs only using 2 cores or 1 core, those are not priority for us, not priority for the scheduler. So it's not that they are not going to be running, it's just that they are given a lower priority in this topic. So all the topics add up. These are so different weights that finally add up into a final priority of the job. So what is this? Yeah. So the quality of service is once the project reached the 100% of the allocation, they can still send jobs to the queue, and the projects can still run some jobs, but after 100% of the allocation, they will not have a normal priority. That's the quality of service. So they will put in the low quality of service. So they will only run in the case no one is asking for resources. So the job can run. And so many projects go beyond the 100% of the allocation because our computer is not busy all the time by projects that hasn't consumed their allocation. So there is always space for keep running jobs. And we capped the maximum they can run to 150%. So beyond that, the projects cannot keep running. Okay, yeah, and there is a quality of service with high priority. So this selected by users. Yeah, so you can choose your quality of service. So then your job, if it's urgent, it can go with a high priority in the queue and execute earlier. Yeah, there is even a highest quality of service that is only assigned by us. Okay. So jargon in Slurm. So the Slurm cluster is the supercomputer. So in this case, we used to have many small supercomputers, but now we only have Setonix and Garawala. Topaz is not here anymore. But Setonix is a cluster, and Garawala is another cluster. Now the partition is a subset of the nodes available. So as the schematic is doing, so these are all the compute nodes. But now you group them. So when you submit a job, you need to choose in which partition. So in this case, for example, if this was all the resources available, you cannot run a job using the 16 nodes at the same time. So you can only execute a job sending it to the blue partition, and that maximum can run into nodes, or to the yellow partition, which only has 3 nodes, and the larger one, which is the green partition, has 8 nodes. Something like that in Setonix, but with many nodes each partition. So we have, yeah. So this is part of the out of date numbers. So these are the Setonix partitions: work, debug, high mem, long, copy, and these are only for the CPUs. We also have the GPU partition, the GPU dev, which is the equivalent of this one, but for GPUs. So for GPUs partitions, we have the working partition is named GPU, the debug partition, which is for testing and developing code, is GPU dev. There is also the GPU high mem. Yeah, I think so. So sorry for this. This slide needs to be updated. And also the work partition, this is referring to the CPU in this case, it's saying 316 nodes. It has much more than that. So we can check that in our documentation. The numbers should be up to date. Debug partition, that's, I think, correct. I think only 8 nodes. So it's used for compiling, testing, and development. One thing is the maximum time for the debug partition is just 1 hour. Um, yeah. So the problem is I jumped to modules where I talk about the allocation. But the thing is, yes. So in the allocation you have, let's say, 3 million service units to be used by the project in the year, and that is given to the projects just in quarters. So you cannot consume everything in the first quarter. You only can consume a quarter in the first quarter, another quarter the next quarter. So that's the idea for the allocation of the year. And yeah, so the more resources you use in the job, the more allocation resources granted are consumed. So the basic units is, if you were granted a million service unit, that means that you have 1 million hours to be run in a core. So service units is exactly equal to hours in a single core. So for example, if you run a job with 128 cores, like using a full node of the CPU nodes we have, and you run it for an hour, then you are consuming 128 service units. If you run it for 10 hours, you are consuming around 1,000 service units. And you have up to 1 million to consume. And if you run a job with 1,000 cores to be used, and you use them for 1,000 hours, well, 1,000 hours is much, for 10 hours, so 1,000, that's 10,000 service units. That's the thing. And yeah, and that keeps consuming. So you will consume your allocation. So minimal allocations that we are giving to projects are 1 million service units. So there's 1 million service units at least for each project to consume in the supercomputer. Yeah. So these are the different partitions, and they have different purposes. So the work partition is the main one. That's the place to run your jobs. For debugging, the debug partition. High mem partition is that these nodes have much more memory than the regular nodes. So the high mem partition only has a few nodes, but just in case you need a job that needs a large amount of memory per node, you use the high mem partition. There is this long partition that allow users to run jobs larger than 24 hours. Some codes are not ready to do these checkpoints, and they need to run beyond the 24-hour limit. So you can run in the long partition up to 96 hours. If you need to go beyond that, you are in trouble. We are here to help, but basically codes need to be prepared to do checkpointing to be really ready to run in a supercomputer. And the copy partition, there are 8 nodes. As I mentioned, this is for doing data transfers when you are in Setonix. You can execute a job that is going to grab data from somewhere and bring it to Setonix, or from Acacia and bring it to the scratch. So you use the copy partition for that, and the partition for the astronomers. Okay, So how many partitions are there in Setonix? That can be seen with the sinfo command. Let's do this. So sinfo. That gives you a lot of information because we have many partitions. So the header is here. The first word is the partition, then if it's available, the size, the maximum size limit, the maximum time, how many CPUs are available. This one is sockets, cores, and hyperthreading available in the partition. So sockets is almost the number of CPUs in that in the nodes. So two CPUs that each of CPUs has 64 cores. Okay. Now number of nodes is the number of nodes relative to this line of the information. So in this line, this is referring to one node in the work partition that is in an invalid state. 7 nodes in the work partition are planned, I think, are planned to be used by a job that is going to run soon, but are not in use at this point. These are in maintenance. We have 49 nodes down from the work partition. This one is sort of restarting, is drained. These other 74 are in maintenance. So none of these are in a good state for work. Here are 10 that are reserved, that I think are reserved for us, at least some of them, for this training. Mixed 260 nodes are in the mixed state and running jobs. Mixed mean that some of the resources are being used, but not all of them. Or in the work partition, that means in the CPU nodes, of the 128 cores available, probably, well, some of them, but not the 128, all of them are being used. So yeah, the scheduler can schedule jobs in the same, like several jobs in the same node. So if one node only needs 40 cores and the other job only needs 80 cores, those two jobs can run in the same node. And if there are still some resources available, they appear in the mixed. So this means that 260 nodes still have resources available, but 902 are fully allocated. So no resources available. The 128 cores are being in use. So that's all this is for the work partition. Then comes the long partition, the copy partition, the ASCII partition, the debug partition. Here are the GPUs, the GPU partition, GPU dev, GPU high mem, and the CASA partition. So there you go. Those are the partitions, and different information appear. One is that is very important. So if you are looking for resources, so mixed without any asterisks or anything, mixed means there are some resources available in these nodes, allocated, nothing. But if you see idle, those are nodes that are completely available, all the resources, no one is using them. So for example, these 11 nodes from the ASCII partition for the radio astronomers are not being in use. There were no idle nodes for the work partition. I didn't see anything. There are 2 idle nodes in the high mem. Not everyone uses them all the time. But here in the GPU partition, so GPU partition has, here it is, it starts here, some are in maintenance. 93 of the GPU nodes are fully allocated. 2 of them are mixed, and there is only 1 idle for a job. So there is some space to run there. 23 are down. For in the GPU development partition, there are 5 idle nodes that can be used. So that's the information there. Yeah, so idle mix down maintenance. Yeah, yeah. To be honest, I don't know what is the difference with the different signs that appear there. Um, yeah, but it's something that we can check. I think the asterisk in the name is that's the default partition. So if you don't specify the partition that you're going to run, then it's going to run with that one that has the name asterisk. In this case, the work partition is the one that is intended. But usually the recommendation is to always tell which partition you're going to use. Okay. So the queues. So sinfo is to query what is happening with the partitions. So an SQ is to query what is happening with the jobs. So let's check. So let's not do that demo right now. I just want you to submit a job. But copy partitions work. Okay. Yeah, I guess it's better if we go to this, and we're going to check the queues with this exercise. So the exercise says go to. I will put this in the chat. Okay, so it is, you need to git clone. Well, go to my scratch and then do git clone that. So cd dollar my scratch git clone. So there are some exercises already prepared there. So cd supercomputing training. And what else? Job scheduling overview and submit first job. So cd job scheduling overview and the first job. I'm going to take a look into this file. So if you edit the file, you can take a look into it. So here, the way we give instructions to the scheduler is via these sbatch lines. I call this the header. So the script has a first header that indicates that it's going to use this shell in Linux, the bash shell. and it's going to start as if you were logging for the first time into the computer. So that means you get the modules clean, the default modules assigned, etc. So yeah, that's what you do in the first line. And then with the sbatch commands, you indicate some things to the scheduler. So these ones are not important for the scheduler, I think, but important for you. That is the job name. But this one is important for the scheduler, where you're going to run this job. It's going to run in the work queue. How many resources are going to be used? So in this case, how many tasks um, that's related to the number of cores that are going to be assigned. Then how many tasks per node, that's related to the resources. So basically, you're going to execute in one task per node, and one CPU per task. So at the end, basically you are asking for just one core, and it's going to run in just one node. And this one is the time limit that the job is going to do. So in this case, is hours, minutes, and seconds. So this job is going to run in 2 minutes. So because of the low amount of resources, this job should go through the queue quickly. And even if not using the reservation we have for the resources reserved for us, if it goes to the normal work partition, as you remember, there were many mixed nodes there, and at least in each of those mixed nodes, there is one core available. So these jobs should be able to go through. And the job is just doing asking for the date and should be sleeping sometime, so we can see it in the queue and then end the date. So let's see. If you have any questions, just let me know. So the first command I'm going to do is to submit this. So you do sbatch, first job. So I received a message. So job was submitted, and this is the job ID. Now I'm going to use the SQ command. The most important command I use is SQ myself. So what is being queued or executed for me, for my account? So this is saying that the job that was submitted, this is important, the state is running, the start time and the end time. So the reason is when your job is not running, and it tells you why. But once it's running, there's no reason at all. The user, the project, the name you put in the script, the node that is executing the job, how many nodes. So that's it. That's the information you get from SQ. And that's the importance of SQ. So let's, if I execute SQ again, it's still running. I can submit the job again. That's going to be another job. So it's the same script that is going to do something, and the same script that is going to do something. So then I can ask what's happening with me. And yeah, the two jobs are running. So let's try something different. I don't know if you have any questions up to here, but if I go to edit the script, well, I will copy first job to second job. So now I will ask for 280 tasks, and the number of tasks per node are going to be 128. So that is 10 nodes. Let's try 100 nodes. So I know this job is not going to go. Is it fine to put the script in another file and then call bash to run that file? Yeah. If what you mean is you create a script and then that script being called by another script, that's fine. You can do that. So you don't need to send your job manually. So I'm doing it manually, but the sbatch command can be a command in a script. So you can do that. We do that all the time. So I'm going to submit the second job. Requested node configuration is not available. I don't know. Probably I didn't do the right maths. Okay. Yeah, probably something that has to do with the memory. Let me try this. So this other indication for the scheduler is that I don't want anything else running together with my jobs. So because I'm using 128 cores in each of the node, I know no one else will use it. But because I received this error message, probably I needed to add this exclusive. So let me check. So let's batch second job. Oh, yeah, now it went through. So the problem is that it was considering it was going to be a shared node, a shared job. And problem is that it calculates the amount of memory needed, and sometimes it gets, you have this problem. So it was not a problem with what I put there. It was a problem with the calculation the scheduler is doing for my job. And it was sort of asking for more memory than required after the scheduler did the maths. But when I put that it was going to be exclusive, then it doesn't need to do the maths anymore. It will try to find full nodes for me for that job. So let's see what the SQ is going to do. So SQ, it's running. That's the first job. I don't know. Okay. Yeah, it ran. Yeah, but I'm trying to create a job that yeah, as you can see, I asked for 10 nodes and it's running. So there are some resources available in Setonix. Let's make it larger. And ask for more. That's 100. That's 1,000. So in this one, I am asking basically for the whole computer. So now let's batch second job. It has been submitted. Now I'm sure that there's no space for my job to run immediately. So now, as you can see, if I should have named, I didn't edit the name of the job. This is confusing, but this is the second script. So it's asking, as you can see, for 1,000 nodes. I didn't change the time, so it's in theory it's going to run only for 2 minutes. So here it's not has not calculated the start time yet. It is just sitting there in the queue. I don't know when it's going to start. Basically, the reason it's not starting, it's because of the priority. There are other jobs that has priority on the computer, and there's no space for this large job to happen. So now, after a couple of minutes, it kept thinking, saw everything that is in the queue, and it said, okay, 1,000 nodes for 2 minutes are going to be ready to run tomorrow around 1 p.m. Yeah, there is a way of removing this, which I don't know. But if you can check, so you can sort of check, Google it and let me know, and I can execute the command to remove. If you don't like this, I can change it. But yeah, I usually don't change the prompt. Okay, so that's the way using SQ. You can use SQ to check for more than just only yourself. So for example, in our case, we check what other users are doing. Just let me check here what else was for the SQ command. So SQ head, so you can check the other jobs too. This idea is to check what is running in the different partitions and what is happening. So we are not going to do that. Basically, the more important thing of the queue is SQ for yourself. That's what you care. So one thing also with the sinfo, you can check for info only for one specific partition. So you can check what resources are available for the GPU, for example, for GPU dev. And then instead of all this big list, you want to know if you can work in GPU dev now. So you can do that now. So just for a specific partition. And here's the short list just for that partition. And you can see that you cannot work there right now. 5 have been allocated, 12 nodes are down. 1 is drained, means sort of restarting. And 2 are in maintenance. So the GPU dev is sort of not ready for you to do anything there now. So that's sinfo and SQ. Yeah. Okay. Yeah. Yeah. Okay. I will stay with this prompt and try tomorrow maybe. Okay. So that's the first part of the scheduler. I don't know if there are questions here. So basically the two main commands we are doing here is sinfo and SQ. And this main idea of the existence of partitions for the scheduler.